In this video, we will talk about how to write your own shellcode and also how to exploit a Stack Overflow vulnerability with your customized shellcode. Remember that in last week, we talked about buffer overflow vulnerability and we talked about one way to overwrite the return address and fulfill the functionality that we want is to overwrite it and then point that to a function that we want to achieve. For example, in our last week's in-class lab, you can overwrite the saved return address to function record so that you will be able to log your participation in class. However, there are many times that such functions do not exist. So the question is, if such function doesn't exist, then how can we execute something that we really want? So one way to look at that is to use a thing called shellcode. In this case, instead of rewrite the return RIP to a function pointer, we're going to just rewrite the value with the address of the path, or say a buffer, that stores the shellcode. In this case, when the vulnerable function returns, the saved return RIP will be copied back to RIP. In this case, since the address is going to be the shellcode start, RIP will start to execute starting from the shellcode address, which we put into the saved return address. So shellcode are instructions you hope to execute. This is like the assemblies that we write. In this case, they're not actually assembly, they're the bytecode representing the assembly for a specific architecture. So the question is, what do you want to execute? Usually, you can get the shellcode from websites such as Shellstorm. You can also use the shellcode from the Python's Pwn library. And here, as you see from the Shellstorm's web page, usually those shellcode can be get the shell one or fulfill a specific purpose such as set REUID or change mode. Get the shell is a very common one. It means that we want the shellcode to execute a shell so that the attacker will be able to get the shell and interact with the victim machine. Of course, there are other purposes that you can use, such as you can use the shellcode to read a secret file, such as the flag file, which you will see in our assignment or in our in-class lab. If you look at the web page that I show you again here, even for shellcode with the same purpose, you'll still see different kinds of them. So the question is, why are there so many different kinds of shellcode? This is because that sometimes shellcode has to meet special conditions. For example, a common condition is that shellcode cannot contain a new line or zero character because the shellcode is copied to the stack using, say, stir copy. Another case could be the shellcode has to be human readable, or say it's printable. For example, in our in-class lab, if I add a specific condition saying that user's input has to be either digital or alphabetic, so if you have a shellcode with other bytes, it will not be able to copy paste to the buffer and it will not be able to trigger the vulnerability. Another possible cases for shellcode is that the buffer may not be long enough to keep the shellcode. So sometimes you have to have a much shorter shellcode in order to fulfill what you need. And in fact, if you look at the vulnerable code, we will notice that there are two different milestones along with the exploit. The first one is what we call time of triggering. That is the moment that the attack input is copied into the buffer and the return address got overwritten. However, right after the got overwritten, it will not jump to the saved RIP immediately. There might be more codes that are executed before the function returns. And the shellcode will not be executed after those code finishes and the function check returns. And the time that function returns is the time of exploiting. That is the moment that our IP is really controlled by us and shellcode will be executed. So any code between time of triggering and time of exploiting may change path or may check path. So we need to be careful when we pave out the input so that by the time of exploiting, the shellcode keeps exactly what we want. So there are many ways to get shellcode. As I mentioned, you can copy-paste shellcode from online shellcode database or from Ponlib's shellcraft package. You can also just write your own shellcode. There are two ways to write your own shellcode. One is to write disassembly, and the other is to write the C-like code. And for either case, when you compile it, you can use GCC, and then after you compile it, you can get disassembly using objdump. So you can do objdump -d followed by the compiled binary, and you will be able to get disassembly and more importantly, the bytecode. So disassembly really doesn't help because you're not going to copy paste the disassembly onto the input. But if you have the disassembly, you will be able to map the disassembly with the bytecode so that you can ensure that the bytecode that you want is what you need for shellcode. Here, I'm going to provide two methods to compile disassembly. One way to compile it is to use NASM. This is an example that you can write and compiled by NASM. There are three sections in the assembly. The first section is the .data section, which stores initialized variables. And the second section, which is .bss section, uninitialized variables. And the last one is .text section, and this is the actual code section. And you usually want to start the .text section using global _start, and from _start label, you can start to write your assembly. Another approach is to use GCC. And similar to the first method, you still need to define the .global session with the _start label. After the _start label, you can start to write your own code. And here you could put .intel _syntax note prefix to specify the syntax for you to write the assembly. You can also define the argument, those variables, by having a specific label with the definition, such as message that I show over here. And to compile the entire thing, you can just save it as an .s file and then compile it by gcc-no-sdlib-static. All right, now let's play with the demo. Suppose that we have a vulnerable program, which I show on the left. And in this vulnerable program, function main contains a buffer overflow vulnerability on stack because of function gets. Attacker can just send an arbitrary long string so that it will overwrite the return value of function main and triggers the buffer overflow vulnerability. Now, let's work on this together and try to exploit this vulnerability on function main of program vol.c. So what I've shown on the right is the attack code that I wrote, and I will walk you through this attack code. Let's actually start from the bottom of it. So here, we first start the process using pong package, and we can just call pong.process to start the process of the vulnerable program. And then after that, we send a string, which will trigger the vulnerability. And we will then start to interact with this particular service using the shell that we created in the shellcode. Before I talk about the layout of this input that I sent to the vulnerable program, I'll first run this and show you how it works. Now I'm going to run the attacking script using Python 3. So it says that it start a process with the PID of 11690. And then because we are using interactive function, it will say that it switches to interactive mode. And now if we just run some command, it will say it will return the command. And then we can do ls. We'll still return the value. Okay, now I'm going to exit it. And then let's take a look at the attack again and understand how we come up with the input that will be able to exploit the buffer overflow vulnerability. And on the other panel, I am going to run the attack script again. And the actual purpose is to run the vulnerable binary so that we can use GDB to get the stack information from the binary. You can also just run GDB with the vulnerable binary. But now I'm going to show you another way to debug, which is to debug a process. So after we launch the attack script, it will show the PID number. And now we're going to do GDB, and then we're going to attach to this particular process. Okay, now attached to the process, so we see that currently we are in the function of read. And let's just use op and see what's happening over here. All right, here is where we are. And let's take a look at the stack. So this is the stack frame for function main. And then we see that here is where our SP is pointing at. And for us, we need to get the address of the input buffer. So we need to locate the argument of function get. So if we go one more down, we will be able to, in the frame of function gets, and what we do is to use info args to get the argument information. And here we see that the first argument of function gets is buff, and it is in the address of this particular one, which ends with the CF0. So now we know that this is the address of buff, and let me just copy it somewhere. I want to figure out where is the saved return address. To do that, we need to go up to the frame of function main, and then we could do info frame. It says the saved RIP is at the address ended with DD38. All right, so now we know the offset between both is saved RIP, and let's calculate the difference between these two. Which is 72. Okay, so now we know that we need to put the address that points to the shellcode to the 72th byte of our input. And then next, we're going to construct the shellcode. So here, I copy paste the shellcode from Shellstorm. And I am using the one for XCCV bin.sh. So just copy paste this part to my Python code and then convert that to bytes because I'm using Python 3. So now we know that the address that we point to, if we're going to put the shellcode at the beginning of the buffer, should be equal to the address of buff, which is 7FFDCF0. So we put the address here and we convert that to little endian. So now we have the address, we have the shellcode, and the rest is the padding. Right now, I'm just putting arbitrary characters such as letter A in between the shellcode and address to fill the padding. I'm going to put some amount of A over here. And the way that I decide for the number of letter A's is to have 72, which I calculate over here, the distance between the saved RIP and buff, and then minus the current length of shellcode because I want to take this part out. In this case, I will be able to guarantee that this part of the string will be in the length of 72. And then I'm going to concatenate this string with string address, which points to the start of the buff, which is the shellcode. All right, so this is the code. And let me just run this code again. And here I can just exit and make this exit too. I'm going to run this again and then type who am I or do ls. After I send a text string, I will be able to get a shell because of the shell code, and I will be able to interact with the shell because of the function interactive.